Okay. All right, let's move on to the Galerkin formulation, right? So keep in mind everything that we have done so far is we are in an infinite dimensional space, right? That basically means that our weak formulation or our variational formulation is actually equivalent to the strong form. And they are equivalent, right? Because you actually get the same solution from both. And there are, in other finite element books, actually, there are theorems that prove that you can go from one to the other one, right? You can go from the weak to the strong and from the strong to the weak, showing that they are equivalent statements of the problem. And the reason for that is, of course, we're living in this infinite dimensional space where obtaining the exact solution is still feasible. Okay? But we said that, in practical terms, yeah, we cannot live in an infinite dimensional space. We can't, right? We have so much computational power and so many computational resources, and that's it. I mean, we cannot really do an infinite computation, and so we need to reduce the size of that space. And so that is the whole point of the Galerkin projection. So far we said that the energy space is infinitely dimensional. So what does that mean? Well, that means that essentially my function u can be represented as some sort of infinite sum of terms, phi I of x multiplied by alpha I, let's call it, where this here is my degree of freedom, and these here are just basis functions. That are responsible from spanning my energy space. Okay? But again, we cannot deal with such a function. Doesn't make sense. And so we are going to relax this requirement, and we're going to say, well, I am going to start looking at finite dimensional spaces. So I'm going to take a function space that are not all functions. All right? Maybe I want to deal with just polynomials of certain degree, which is what we do in the finite element method. Maybe we want to deal with polynomials that are higher polynomials up to a certain degree, which is the basis of the P version of the finite element method. Or maybe we want to incorporate, in addition to those, we want to add some functions that become singular at a point in the domain, right? And that is actually the basis of enriched FEM, right? In enriched finite element methods, we deal with these more advanced functional spaces. So we expand the set of functions that we like working with because we find a way to work with those functions, right? Integration sometimes becomes a little bit harder, but we can still work with them. So we're going to relax this requirement. And so we look for a solution in a finite dimensional space. And we're going to call that EH of omega. And we denote that it's finite dimensional because we're going to say that that is a subset of my energy space. Remember that is infinite dimensional. And again, H, remember that with H we denote, what do we denote with H? Mesh size. And so we are already, every time that we see an H in a symbol, we know that we're dealing with a discrete functional space, right? We are dealing with either a finite element discretization or it is discrete in some form, right? That's what we have to think of when we look at this H. And by doing so, we are going to accept there may be an error. And I said there may be because we may be lucky enough that it just happens that we pick a very simple functional space, but it still yields to the exact solution. So for some very simple problems, that still happens, right? For instance, there are in the book there are a few examples where you have just one force applied at the end of the bar, and there is no force per unit length, and then the other side of the bar is clamped. Well, it just happens that I know that my exact solution is a bilinear, and I can capture that solution with the finite element space that I chose. So you may be lucky enough that you can still capture the exact solution, but for the most part, that will never happen, okay? In 1D, you can still hope to get the exact solution of problems. The moment we move to 2 dimensions, to 3 dimensions, getting the exact solution is nearly impossible. With exceptions here and there. Again, there are some configurations, a square plate. There have been in the past people proposing certain problems for which they find an exact solution, but for the most part, you just have a little complication in the way your model geometry is created, or you have a feature, a special feature. That's it. The exact solution is no longer available to you. Okay. All right, so if we accept that there is going to be an error, right, we know that we don't get the exact solution. Well, as we said earlier, as long as we can control that error, we can really get a good solution. How good? Well, good enough that we can work with it, right? And so when we change the problem, when we project to a finite dimensional space, now the structure of the problem becomes slightly different, right? Because now the finite dimensional form of our weak form is find UH. Now, of course, that's going to belong to that finite dimensional space, such that, and I'm going to write again this in abstract form. For all WH that belongs to that EH of omega. Okay? And you notice that the abstract form doesn't really change, except I put an H in every symbol. That means that already I'm in a finite dimensional space. We are no longer living in infinite dimensional space. That means that this problem structure is essentially different than the strong form already, and also the variational form. It's a different problem, right? Now we can solve this problem. We just have to pick what is going to be UH and what is going to be WH. We plug in those functions into this form, right? And that process is going to yield the discrete equations that we're going to be solving in the computer. When we do number crunching in the computer, this is exactly what we're solving. All right? And so if UH and WH belong to the same space, right, we call this Bubnov-Galerkin projection. Bubnov-Galerkin. Otherwise, we call this Petrov-Galerkin. Okay, and well, why would you choose a Petrov-Galerkin formulation? Why would you take these functions from a different space? Well, it turns out that in the past, people were unable to solve for fluid mechanics problems with finite elements. Okay, and there were issues with instabilities. The moment you had advection terms in your formulation, and those advection terms were very important, people noticed that the Bubnov-Galerkin was not dealing with those problems effectively. And so someone said, well, let's try to choose these functions from different spaces, right? And so that was the basis what it became the SUPG, or the streamlined upwind Petrov-Galerkin formulation proposed by Tom Hughes many, many years ago. And then suddenly that opened the field so that you could actually solve for fluid mechanics problems using finite elements. Otherwise, people use, finite volume, finite difference.
What does it mean if you say they come from different functional spaces?
Yeah, so what I mean is that UH has certain form, and WH has a different form, right? They are different functions.
Does it mean that those spaces are disjoint in some sense? Or
No, it means that the spaces are different, that the functions that you choose are not the same, okay? And obviously, that has also consequences. So what happens to our symmetry property?
will go away?
It will go away, right? Now, my system no longer is symmetric because I cannot just simply swap those two, right? In the resulting problem, when you have advection terms, then that symmetry is lost. And obviously, with the loss of symmetry, you have to use other tools to solve for the problems. You cannot use certain solvers like Cholesky factorization. Well, normally, actually, we don't do direct solvers, but we do iterative solves. But the problem becomes more complex, okay? Okay, but I want to spend some time talking about the property of the Galerkin projection. So we're going to look at the orthogonality of the Galerkin error. And so if we write down again the main variational form that we obtained earlier, if you remember, we said, well, B of UW has to be equal to L of W, and that had to be valid for all W in some space that we call the energy space, right? But if it has to be valid for all the energy space, right, all of it, certainly it has to be valid for a subset of that energy space, right, that we call EH, right? Again, this function is valid for all the space, all the energy space, all possible functions that give you a finite strain energy. Therefore, it has to be valid for a subset of that space that we call EH, okay? And so we can write B of U WH is equal to L of WH. And again, this is valid for all WH that belongs to EH. And again, that is the case because this EH, again, is a subset of the energy space. All right? Okay, now we can write the Galerkin projection. And the Galerkin projection is saying, well, I know also that my UH is equal to L of WH. And again, that has to be valid for all WH in my discrete space. Yeah. Now, if I take these two expressions and I subtract one from the other, I get an expression that says U minus UH WH is equal to 0. And that has to be valid for all WH in my discrete or finite dimensional space EH. So what is this saying? If I define this here, what is that?
It's your error.
It's your error, right? Because I know that U is my exact solution and UH is the approximate solution. So that is the error that I incur by the approximation. This is my error. Okay? So what this expression is saying is basically that the error, in the sense of the bilinear form, right? My error is orthogonal to the entire space, the discrete space that I chose. And there are many ways to see this, okay? So I'm gonna write a few statements, and they are in a way all equivalent. So the error is orthogonal to the subspace E of H. Of course, we are dealing with respect to the bilinear form. because obviously when we're doing this derivation, we're looking at the bilinear form. Another way to see this is that UH is the projection of the exact solution onto that space EH. And another way to see this is that from all WH that belong to that finite dimensional space, we pick UH so that that product is equal to 0. It's like a dot product. Remember, we look at this also in nonlinear mechanics. The moment you take your weight function and you multiply by your differential equation, that is basically a product. It's a condition. The moment you say that that is going to be equal to 0, you are saying somehow that your test function, right, has to be in a way orthogonal to that differential equation. So when we solve this problem, actually we pick what would be our UH that is going to make that condition happen, so that these two things become orthogonal. In other words, I pick UH so that this whole thing becomes, that orthogonality property holds, which is something incredible. We pick the best solution. From all of the solutions in that space, we pick the best one. And of course, there is a theorem that proves that again in the book chapter is called Say's approximation theorem. UH is the one that minimizes the error. Okay, well, let's try to see this, and of course, when we want to see something with functional spaces is very hard. So we do an analogy, right? So we have this vector space analogy, and keep in mind always, please, that this is just an analogy. So say you have your exact solution somewhere. It's a 3-dimensional vector, okay? So my U is U, and I'm gonna say, well, U is in R cubed. It's a 3-dimensional vector, right? And somehow I have this plane. This is R squared, and now essentially that is going to be my EH of omega, right? So I'm going to be dealing with 2-dimensional vectors where I know that my exact solution lives in 3-dimensional space. Well, what the Galerkin projection does is basically finding that vector, so that my UH so this here is U minus UH. U minus UH, we said, is the error. So that basically means, I'm not sure we see it properly here, but the idea is that that vector is orthogonal to that plane. So we project our exact solution into that plane where I'm looking for all vectors. And notice, it could be any vector, right? It could be that vector, it could be this vector, it could be that vector, it could be any vector. Any vector, there is, how many vectors are there in that plane? Infinite number of vectors. And yet the Galerkin projection is picking this one. And again, there is a nice theorem that proves this, which is something crazy, right? Like, the Galerkin projection is, to me, one of the best things ever invented, because it allows you to get something from infinite possibilities. It gives you the best solution that you can possibly get. And that is insane. And it all goes back to that relationship that we wrote. Okay, let's write the weak formulation. My variational form says, okay, my W, my test function, is not only a function, right? It's a function space. So somehow I write down an orthogonality condition between a function space and my differential equation. And I say, I want these two things to become orthogonal to each other. So give me what would be the UH that is going to make that happen. And it turns out that the projection is the best possible solution to that. You have a question?
Yes. So in fact, we have a unique solution, because the
Yeah.
and goes to that particular point is just one.
Yeah, you have a unique solution. Remember that we have a unique solution as long as certain things hold, right? There are problems for which there are an infinite number of solutions. We talk about pure Newman problems, right? If you don't restrict the rigid body motion of the bar, you're gonna get the solution up to a constant, right? So you can get the strain in the bar and the stress, but the exact location in space is irrelevant, right? We didn't prescribe any displacement, yeah?
So the magic of the Galerkin projection is the fact that you are trying to find minimal error, and by finding an orthogonal vector, you find the shortest path of projecting that.
Yeah.
Therefore, you also find the minimal error.
That's another way to state this, yes? And indeed, it is magical. Indeed, yeah?
What I don't get is how you restrict the functional space. So if, for instance, if you have the finite energy space,
Yeah.
and that consists of functions, and then if you transform that to a subset, namely to the
Yeah. Yeah.
discrete form of that.
Yeah.
I'm trying to imagine in my head what kind of functions are in E omega but aren't in EH omega. So is that how do you make that discrete? Because
Pick up any function you like. Remember, when we look at this expression here, these basis functions could be anything.
Yeah.
Trigonometric functions, exponential functions, it could be polynomials, of course, right? Any function you can possibly imagine can enter there. And there are, of course, more complicated functions. You can have functions that combine functionals. You can have anything you want. And yet we normally look at this from the other side. You say, well, let's start with functions that are nice to work with, and that is the reason why we start using polynomials. Yeah? Yeah?
So for the energies, for the discrete energy space,
Yeah.
then must be, of course, a subset of the whole energy space. But in order to relate it to the actual body,
Yeah.
in this case, the body itself will also be discretized to match the discrete energy space, right?
Okay, now you are going into the finite element discretization, right? And so now that we say we are going to be dealing with polynomials, say we want to deal only with linear polynomials. Now, of course, the space, the actual space that you use is going to be defined also by your nodal discretization, right? So if you divide your bar in two elements, right, you're going to have a bilinear solution that is going to be different than if you divide your bar by 10 elements.
Right.
Yeah. So the spaces are going to be different, right? In one case, you have 3 coefficients. In the other one, you have more, right? But the class of functions remain the same, right? But the spaces are different. So the discrete spaces are different. So obviously, dealing only with linear polynomials, you can also have so many different variations of how you define that space. And again, that is also the basis of this convergence analysis, because given a set of functions that I choose, linear polynomials in this case, right, I'm going to increase the dimensionality of that discrete space from this number of terms, let's say 2 terms, 3, 4, and so on, and then I see how that energy norm is going to reduce the error with respect to the energy norm. Yeah.
So the more elements of the bar, it will therefore decrease the amount of UH, right?
Decrease the amount of UH?
Of error per se, but like,
yeah.
How would it change the UH?
Yeah, so of course, the more, you may argue that the more freedom you give to the definition of that space, the least the error. You can imagine that, right? Always, the more freedom you have of choosing, the more computational cost it's going to take to get to that solution. But you would expect also that the solution is going to be slightly better, right? And that is, again, the basis of this H version of the finite element method. In a way, what I just said also applies to the P version of M, right? Because say you want to go from cubic to quadratic, you didn't change the mesh, but you are increasing the dimensionality of the discrete space, right? And well, if I'm putting more effort to get something that has one higher degree polynomial, I would expect to reduce the error.
And
right?
in the Euclidean analogy, it would be, instead of a plane, you would also have a cube, for instance. So you would change the number of possibilities you can get for UH increases, right?
Well, in this analogy, you don't really see that because it's higher. It's very difficult to see things in higher than 3 dimensions, right? But you can think instead of a cube, yeah, you can try to imagine that you go from 3 dimensions to something that has 4 dimensions, and of course it's harder to see, but that would be the same idea, right? That you can increase the dimensionality. Say your exact solution U doesn't live in 3-dimensional space, but it lives in 10-dimensional space, right? Now it's impossible to see it, but you can think of that as I am taking my UH from increasingly higher Euclidean spaces, so we go from 2 to 3, 4, 5, obviously I should be able to represent that 10-dimensional vector in a much better way. So that would be the same analogy. Okay? Yeah?
Does the function also, so the Galerkin formulation, does that also optimize the dimensional size of the solution? So for instance, if you know that, let's say a solution with dimension 3 is optimal, is that being optimized in that form as well? That it also automatically chooses a polynomial of n is 3?
Yes, exactly. And in fact, you can see this, and actually in the project you can actually test this. Say your exact solution is a quadratic polynomial, right? And then, well, solving the problem with a quadratic approximation is already giving you the exact solution. So what happens if you add a cubic polynomial? What would happen? Keep in mind that the Seas approximation theorem still holds, and you are still going to get, when you solve a problem with a cubic approximation, you are still going to get the exact solution. So what is the Galerkin projection going to do to your cubic polynomial?
Do it faster.
Oh, it reduces the final coefficient probably to 0.
Yeah, exactly. Exactly. Right? So you add something in the hopes that it's going to improve, but you already got the exact solution. So the Galerkin projection is still going to tell you, yeah, this is not good. It doesn't really help you in improving the error, so it's going to zero it out.
Yeah, alpha 3 will be 0 then.
Exactly.
And if we go back to the definition of UH further up, further, yeah, it's that one. The U phi, that one. The Galerkin formulation of U phi equals if we have then the UH of phi.
Which one are you talking about?
You
This guy?
if you have that one.
Yeah.
So for that one, you can clearly see that that's the infinite energy space, the reformulation of U phi, right?
Mm-hmm.
So if we go then to the discrete form of that, so UH of phi, for instance.
By the way, this is supposed to be x.
What? Oh, is that x? Oh,
It's
phi.
x, and this is also x. Yeah.
So if we discretize our energy space,
Yeah.
does that limit the summations assigned to n, for instance? That limits.
There you go.
Okay.
Exactly. So now this term here is not going to be infinite, it's going to be 10.
I see.
And
So-
in the case of a finite element discretization with bilinear functions, for instance, the root functions or the hat functions, right? If we discretize this in 10 elements, what is going to be this number? 10 elements. How many nodes we have? 11. So now our dimensional space, finite dimensional space, is going to be size 11. Okay, let me cut here the video, and we continue informally with all the questions, okay?